Today in this video we'll be focusing on Coulomb's law. And Coulomb's law describes the electric force that one stationary charged particle exerts on another stationary charged particle. Applying the law is pretty straightforward arithmetic, but difficulties tend to arise for many students because this is the first exposure many students have to having to use vectors. And vectors can cause problems involving how to decompose them, the plus and minuses, the sines and cosines, drawing the vectors, adding them, subtracting them, etc. So I'll be focusing on those aspects of the problem today. And let's go ahead and take a look at the problem statement. So here's a sketch of the problem. We have three positively charged particles. Each of them has a charge of 20 microcoulombs. They're all separated by a distance of 1.5 meters. And what we're asked to find is the force that the first charged particle feels due to the presence of particles 2 and particle 3. And we know this is a Coulomb's law type problem because these are all charged particles, so this is an electric force, and they're all stationary. So the approach here will be to find the force that the first particle feels due to number 2 and then number 3, and then add those up as vectors. The Coulomb's law states that the force magnitude is given by this formula, so it's going to be a constant times the product of the charges between the two particles divided by the distance between them squared. The direction is going to be given by, well, if they're the same sign, they're going to be repulsive. If they're opposite signs, they're going to be attractive. To get an idea before we do the computation of what the direction and the force actually look like, let me just draw the vectors representing the forces upon particle 1. So if I just redraw particle 1 down here, and I want to find the force on it due to particle 2 and then particle 3. So the force from particle 2, well, first of all, are they the same sign or opposite sign? They're the same sign, so that means they're going to be repelling, which means that particle 2 is going to be pushing particle 1 straight upward, directly away from it, in other words, radially. So it's going to be pointing straight upward. Right, so you have a force. This is the force vector representing the force upon charged particle 1 due only to charged particle 2. And I'm going to call that F21. And I put that arrow on top to indicate that it's a vector, so I have to keep in mind not only its direction but its magnitude. And then we're also going to have a force that the particle 1 is going to feel from particle 3. That's going to be going, again, these are the same signs, so it's going to be repelling, so it's going to be going up and to the left. It's going to be pushing it up that way. And it's the same magnitude because particle 3 and particle 2 have the same sign and the same distance away from particle 1. So this formula would give you the same number. So to reflect that, I'm going to draw them as the same magnitude. And that's generally a good idea to get an idea of the magnitudes because that kind of tells you when you add these vectors up which direction it points in if you have good relative magnitudes. Now, let me just make clear that these are not the only forces upon this diagram. There are other forces here. For example, Q3 feels forces due to Q1 and Q2. And these forces point down and point that way. But we're not asked to find the force upon Q3, nor are we asked to find the force upon Q2, only upon Q1. So only draw those forces and only add those up individually. Don't worry about the other forces. Now, to find the net force, if you add these two vectors up, so to add vectors, you always line them up head to tail. So you just draw them consecutively, one by one, head to tail. So F21 points straight up, F31 will point in this direction, and I'm just going to line it up so that this tail lines up with this guy's head of the arrow, which would be like this. And then the net force will always be from the very beginning to the very end, which looks like this. So we should find eventually, once we do the computation, that the force vector should be kind of going up in that direction, and its magnitude will be longer than the magnitude of these two guys individually. We'll come back and make sure that's the case when we actually find the number for this. But let's go ahead and carry out the computation first. So we know that the net force upon charged particle 1 equals a force from 2 upon 1 plus the force of 3 upon 1. And I'm being very careful to draw the arrows on top of these vectors to indicate that this is a vector equation, not a scalar equation, so we have to decompose it into x and y projections first before we add anything up. What that means is we have to find the components of F21, and we have to find the components of F31. Before you can find components, though, you have to find a coordinate system. You have to define your coordinate system. And you can define it as you wish. Usually you want to define it in such a way to make things easier for you. And that's always the case if you have as many vectors lining up along the axes as possible. So we have a couple options here. These are the two vectors we're going to be adding up, F21 and F31. And so I want to choose my axes such that I have as many of those vectors lining up along the axes as possible. And I can't choose it so that they all line up because the axes have to be perpendicular. So I could choose it like this. F21 points along y, but then F31 is along some weird axis. I could choose it like this. Now F31 points along y, but F21 I have to decompose. You can choose it in some other ways, but no matter how you choose the axes, you're always going to have at most one vector pointing along an axis. I'm going to choose it like this because it's a little less traditional. Usually we're used to seeing it like this. It'll be a little less traditional like this, kind of for practice. So I'm going to choose the axes like this. And let me just draw the axes here. So this is x and y. And what I need to do is write down the components of f21 and f31 in this particular coordinate system that I've defined. Once you define the coordinate system, you can no longer change it. So it's got to be the same for all these vectors. Now let's do f31 first. So let me just draw f31 here. I'm doing this one first because it's trivial, because it actually points along negative x. So its components they're just going to be given by, well, it has a negative x component, certainly, and its negative x component equals the magnitude of the vector. It points directly in the negative x direction. So it's the magnitude of the vector, but it's minus because it's pointing in minus x. And this f31 without the arrow just means the magnitude of the vector. In other words, I would plug in these values here in Coulomb's law to find the magnitude of that. And it has no y component because it's perpendicular to y. All right, so that one's the trivial one. That's the one that I line up the axes to get that one to be easy. Now, the other vector is going to be a little trickier, so let me draw the coordinate axes for those. It's a little off, but these should be the same as that. f21 points straight up, so if I just draw f21 here, you see that it does not point along x and y, so you have to find the components in both x and y. The way to find components is, let me just go ahead and, I'm going to extend this x-axis backwards because the component is on this side. The way to find components is to imagine that you have a light and a shadow being cast upon one of the axes. So let me just do the x-axis first. And imagine the light is coming perpendicular to the axis. Whatever the shadow is, the length of the shadow is that component in that direction. So if the light's coming like this, your shadow will extend down like this, and it'll be this long. And that is the projection of f21 upon the x-axis. In other words, the component f21 in the x direction, which we call f21 comma x. Likewise, along the y direction, a shadow coming like this will make a, or sorry, the light coming like this will make a shadow that's that length, which is f21 comma y. Okay. So now what I need to do is find out how long each of those vectors are. And I can just use trigonometry. So carrying out the trigonometry, if you just inspect this triangle, this angle is going to be 60 degrees right here because this angle is 60. So we're going to have 60 here and 30 here. And then just using trigonometry, we'll find that f21 is going to be given by the x component is this distance, which is going to be the hypotenuse times the cosine of 60, just using trig. And then the way I'm doing this, whenever you use trig to find components, you have to put the signs in by hand. Right? So in this case, we know that it's pointing in the negative x direction. So you're going to get a positive number for this. You have to put the negative in by hand because it's pointing in the negative x direction. And then for the y component, it's pointing in the positive y direction. And its length is given by f21 times the cosine of 30. And it's positive because it's pointing in the positive x direction. So you don't need to add any extra signs to that. Now, you may be more familiar to seeing like a sine here, a cosine here, and a sine here or something. You could actually use this distance as f21y as well. And if you did that, it would give you f21 times the sine of 60. So that may look a little more familiar to you, or one of them has to be cosine and one has to be sine. But this will give you the same number, so it doesn't really matter. All right, so now that we have the components here, we can easily just plug in the values that were given. So what we need to do here is find out the magnitude of f31 and f21. So go ahead and do that on your own. Find out f21 and f31 using the charges given, using the distances given, and then just use the cosine 60, cosine 30 to find out the actual numbers. So what you will need to find out is what is f21 and what is f31 numerically. And we'll come back and add those up and find the magnitude. So go ahead and take a minute and do that now, and we'll come back and take a look. So plugging in the values given for the charges, the distances, and the constants, we'll find that the magnitude of the force, F31, is 1.6 newtons, which is the same as the force F21 because they involve the same charges and distances. So in particular, because F31 is 1.6 newtons, we know that the components of the vector F31 are minus 1.6 and 0. And then likewise, for F21, we're going to have minus 1.6 times the cosine of 60, which will give us minus 0.8. And then for the y component, you're going to have positive 1.39. And these are all in newtons. So those are the two forces. So the whole purpose of this was to find out the components of the forces in both the x and the y directions. Now once we have that, we can add those up individually. So adding up the magnitudes at the beginning is incorrect. You had to find the components in each direction. From there you can add those, and then from there we can find a vector representing the final force. So going ahead and doing that, we're going to find that the net force upon particle 1 is, well, the x component is the sum of these guys, which is minus 2.4, and the y component is the sum of those, which is 1.39, and that units is in newtons. Okay. So before I find the magnitude, which is what the problem is asking for, let me first just verify that these numbers kind of make sense with our picture, because that was the reason we drew the picture in the first place. So we have, let me go ahead and actually write down the coordinate system on this right over here where I have the net vector drawn. So the coordinate system kind of looks like this. Again, the F31 is pointing along the negative x, so it's got to kind of look like that. So we have a y that way, and we have an x kind of like this. All right, so let's make sure these numbers, at least the signs make sense and the relative magnitudes make sense. We have F31, or sorry, we have the net vector is minus 2.4, comma 1.39. And that means that you should have a pretty substantial negative x component and a substantial positive y component, but not as big, which is kind of looks like what we have here. We have an x component. This is the vector we're looking at, the net component. X vector is negative and big, and the y vector is also positive but not quite as big. So at least our picture is consistent with the numbers we found. It doesn't tell us the numbers are right, but at least tells us that if we did find some numbers that have different relative magnitudes or the wrong signs, we need to go back and check our math. So that's always a good check once you find the numbers for vectors. Now that we have the net vector, we can find the magnitude. The magnitude is just the components squared and added up and then finally square rooted. That's just a Pythagorean theorem. And that's carried out in detail in the attached solutions. So let me just go and write down the answer here. The net vector is going to have a magnitude of 2.77 newtons. All right, and so that represents the magnitude of the force that charged particle 1 is experiencing due to charged particles 2 and 3. And again, we had to solve this by finding components and then breaking it up and then adding them up individually. So let me go ahead and summarize in detail what we've done here. In this problem, we were asked to find the electric force upon a charged particle using Coulomb's law. We first drew vectors representing the forces and added as a vector sum to visualize the net force. Then we defined a coordinate system and decomposed vectors into components using trigonometry, putting in the signs by hand. Next, we added the components separately to get the net force vector, and then finally, we took the magnitude of the resultant force vector. Okay, so that's it for this problem. If you have any comments or questions, please leave them on the link attached to the video, and we'll see you next time.